Good morning, everyone. Are you able to access the slides? Good, Shruti. Good morning. So let's wait for 1 minute till others also join. Good morning, everybody. So let's begin our Sunday lecture. So yesterday, I ended by showing this picture in which you see the you see a spiral galaxy. This is the disk of the spiral galaxy. This is the bulge, and these are the globular clusters of this spiral galaxy. And the globular clusters, of course, move in eccentric orbits around the center of this spiral galaxy. So the light that we receive from stars as well as gaseous matter, they come only from this region. So here you have the spiral arms, the bulge, and the stars in the globular cluster. Each globular cluster has about million stars. Globular clusters have older stars. The stars in the disk, particularly in the spiral arms, these stars are young stars, and that's why they appear bright and bluish in color. They are massive young stars. And yesterday, I qualitatively argued from the evidence of the way rotation speeds fall, rather rise with distance and become flat at very large distance from the center of the galaxy. That's how Veera Rubin and her team members concluded that every galaxy is resides the visible part of the galaxy, namely those parts that are made of protons, neutrons, and electrons. Protons and neutrons in high energy physics are called baryons, and that's the reason in the parlance of astrophysics and cosmology, we will refer to the matter which are composed of protons and neutrons as baryonic matter. And baryonic matter, they since they interact with light, their presence can be inferred by measuring light from various parts of a galaxy. But then the flat rotation curves indicate that galaxies are embedded in a spheroidal halo made of particles which do not interact with light. Their interaction is very weak, and of course, the universal gravitation is something that even the particles constituting the dark matter, they participate in the gravitational interaction, and their presence has been inferred only from their gravitational influence on the baryonic matter. Right, but let's also talk about the clusters. As I mentioned yesterday, uh, Zwicky, he made very thorough study of Coma cluster, a cluster, a rich Abel cluster. They contain about 1,000 galaxies. And here you can see one of the clusters having so many galaxies bound to the common gravitational, attractive gravitational potential created by uh, all the matter present in the cluster. And here you can also see the chords of light. You can see the arches of light, and these are created by the gravitational lensing of a source far behind the cluster of galaxy. And the gravitational lensing also plays an important role to estimate the total matter residing in a cluster. So here is a cartoon of a cluster of galaxies which are containing the galaxies which can be seen from the light emitting baryonic matter. But if it has a dark matter halo, then here we are in the Milky Way galaxy, and if there is a distant galaxy or a quasar very, very far away, then light from such a such an object which is behind the cluster, as it travels along, it can get bent due to the gravity of the cluster, and and if it is exactly lying in the on the line that connects the center of the cluster and the earth, then the light which comes out of this quasar or a distant galaxy, they will get bent, and there is a cylindrical symmetry, and therefore a point source here will appear like a ring because of the gravitational bending of light, because the observer here on earth would think that the light is coming from this direction, and similarly this light ray will make the observer on earth um, perceive the source of the light to be in this direction, and therefore a point source which is collinear with the center of the cluster and center of the earth, the point source will appear like a ring. This was discussed by Einstein himself, and that's the reason why such a ring like image of a point source is called an Einstein ring. And in particular, what we see here is uh, these arches of light. They are essentially parts of the Einstein ring, and gravitational lensing, which creates such arches, that tells us about the entire mass, not just the baryonic mass, which are associated with stars and the gas in the galaxy, but entire dark matter by virtue of their gravitating mass. The total gravitating mass causes the bending of light, and therefore, by studying the these arches, one can infer what is the total amount of matter which is associated with the cluster of galaxy. And hence, we can infer about the dark matter by modeling the gravitational lens. Uh, 6 to 8 years ago, astronomers observed the so-called bullet cluster, where two clusters of galaxy they collided. And here, what you see in reddish image, of course, these colors are artificially introduced by astronomers so as to describe what they are talking about. So the reddish color are the regions where baryonic matter have been seen through telescope, while the bluish region is the inferred dark matter from the gravitational lensing. You remember, dark matter cannot be seen in any other wave band. They can be only inferred from their gravitational influence, and the mapping of the dark matter, which is shown in blue, this mapping has been done by how the a source which is behind the two interacting clusters of galaxies, a source behind has been gravitationally lensed, and to describe the lens, the mass distribution has been plotted, and the modeling of the gravitational lens requires presence of mass here, 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 here. But observations only tell us about the mass in this location. Observations don't talk about any mass present, but the gravitational lensing model requires that there be dark matter located in this region, distributed in this region, as well as dark matter distributed in this region, which is inferred by from the modeling of gravitational lensing. Now, this immediately makes it clear that when the two clusters collided and passed through each other, the dark matter went through. You see, the dark matter is found at the extreme region, while the baryonic matter, which are baryonic matter meaning matter associated with stars and gas, they are found in the region which are between the two clouds of dark matter. Now, obviously, this is expected because dark matter, they don't have any other interaction except some tiny weak interaction and gravitational interaction. So when the clusters collided, they simply would pass through. But the baryonic matter, because of the viscosity of the gas, their velocity will get damped out and they will not be able to move further out. So they will be trapped in the region between because their velocities would be damped because of the viscous force, which are associated essentially with electromagnetic interaction. So the bullet cluster information tells us, yes, there is indeed matter which do not have any viscosity. Rather, their influence is essentially inferred via the gravitational interaction. And bullet cluster strongly suggests that there is indeed reality to the assumption that there is dark matter which do not have any electromagnetic interaction like viscous forces, etc. Right. Now, what I will do is I will share with you some simple calculations so that our understanding of dark matter is on firm footing. So what I will do is I will now share some material that I have made. So I'll stop the screen and then I will, yeah. So I hope you're able to see this slide. Before I talk about the calculations, Shubham is asking why color is different for dark matter and baryonic matter. As I mentioned, these colors are artificially introduced. Actually, there is no color. You only see the presence. If you use the telescope, you see the presence of stars and gas through telescope. But the bluish part, which has been artificially introduced, is to give you the distribution of dark matter that is required to explain the gravitational lensing. So the colors are artificially introduced by the astronomers to delineate which are the regions where baryonic matter is present and which is the region where dark matter has been inferred from the gravitational lensing model. Right. So we will now use very simple calculations to have concretely the idea of the presence of dark matter. Okay. Right. So typically, let's talk about the work which was done by Zwicky. Okay. So Zwicky analyzed a cluster called Coma Cluster. So let's consider the rich Abel clusters of galaxies. And typically, a rich cluster contains 1,000 galaxies, and the radius of such a cluster lies between 1 megaparsec to 10 megaparsec. Oh, I made a typo here. The megaparsec is missing. So typically, a rich cluster of galaxy, uh, the size of the galaxy is between 1 megaparsec and 10 megaparsec. Now we have already been introduced to the virial theorem. Virial theorem says that if you have a gravitationally bound system that is in equilibrium and its shape is not changing on an average, then twice average kinetic energy of the bound system must be equal to the negative of average potential energy. And there is no contradiction here because kinetic energy, of course, is always positive. But for an attractive bound potential energy is also negative. So two negatives make it positive. So there is no fallacy, mathematical fallacy in equation number 1. The average total energy of such a bound system will be average kinetic energy plus average potential energy. And by virtue of the virial theorem, since average kinetic energy is minus half of average potential energy, this becomes minus half of average potential energy plus average potential energy, which is equal to half of average potential energy. But because for attractive potential energy is always negative, average potential energy is also negative, and therefore for a bound system as we require, the average energy is also negative. So everything is consistent so far. Now let us apply the virial theorem to our galaxy cluster. So suppose our galaxy cluster has capital N number of galaxies which are distributed in roughly a spherical region of radius r. And the galaxies in this cluster, of course, would be moving randomly, and you can find out what is the variance of the random speed. How do you calculate the variance? Because each galaxy is randomly moving, first you calculate the average velocity by summing up vectorially all the velocities, okay, and divide by n, so that will give the average velocity. Then what you do is take the velocity vector, from that you subtract the average velocity, square it, and then take the average. That will give you the variance, sigma square. So here the dispersion speed sigma is nothing but the square root of the variance of the velocities of the galaxies inside the cluster. Right. So suppose we did not know that the galaxy cluster had dark matter. Okay. And we estimate the mass present in the cluster by estimating the individual mass of a galaxy. An individual mass of a galaxy can be estimated by counting the number of stars, and each star will have an average luminosity, and from the luminosity we can estimate the baryonic mass of a galaxy. So here m gal hyphen bar represents the average baryonic mass of a galaxy. And typically, the average baryonic mass of a largish galaxy, like an elliptical galaxy, will be 10 raised to power 12 times mass of the sun. That is typically the baryonic mass of a galaxy. Now we can estimate the average kinetic energy of the associated with the cluster, because the average square of the speed is nothing but square of the dispersion velocity, and there are n number of galaxies, so each kinetic energy must be summed up, so that be roughly half times number of galaxies present in the cluster multiplied by the mass of a typical galaxy multiplied by the variance of the speed. So this will be the associated kinetic energy of the galaxy cluster. And if you put in the numbers, that is, if you take sigma, the variance to be 1200 kilometers per second, mass of the baryonic mass of the galaxy to be 10 to the power 12 solar mass, and the number of galaxies in a cluster to be 1000, you find that average kinetic energy is about 1.44 into 10 raised to the power 64 erg. Huge energy, right? Look at the numbers. 10 raised to the power 64 erg. Obviously, because we are dealing with a cosmic source, the numbers are also going to be astronomically large. So the equation 3 gives an estimate of the kinetic energy associated with a galaxy cluster. And the way I have written it out, if the number in the cluster changes, you can substitute that number. Similarly, if the mass of a typical galaxy is different from 10 to the power 12 solar mass, you can substitute the number. Sigma, sometimes for a very tightly bound cluster of galaxy, can be as high as 1500 kilometers per second. So all those numbers, if you put in, you can get the number associated with the kinetic energy. Similarly, we can also estimate the total gravitational potential energy of the cluster, assuming that the cluster is totally composed of baryonic matter. So if the cluster mass is M cluster, then we know that the gravitational potential energy is minus g m square cluster divided by the size of the cluster. Because any object of mass m, its gravitational potential energy is minus gm square by r. So if the cluster has a mass m cluster, then the gravitational potential energy is minus gm square cluster divided by r. Hence, since mass of the cluster will be n times mass of a typical galaxy, so therefore average potential energy will be minus Newtonian gravitational constant times n square of the mass of a typical galaxy divided by the size of the cluster. And again, you can show that the number turns out to be that average potential energy is minus 1.8 into 10 to the power 64 erg, and these factors. So by depending upon the cluster, n will change, typical mass, baryonic mass of a galaxy will change, size of the galaxy will change. Here, uh, the size, these numbers correspond to n equal to 1000, typical mass of the galaxy to be 10 to the power 12 solar mass, and the radius of the cluster to be 5 megaparsec. Now, it is obvious that twice the average kinetic energy plus the potential energy is actually greater than zero, is not equal to zero. While the virial theorem would tell us that twice average kinetic energy plus average potential energy should have been zero, here it is not zero, which tells that for these numbers, the system is not virialized. What about the total energy? The total average energy of the cluster will be average kinetic energy plus average potential energy. Here, although it is negative, minus 0.36 into 10 to the power 64 erg, but if, for example, if your mass, typical mass of the galaxy was less than 10 to the power 12 solar mass, then you will find that the total energy would turn out to be positive. Okay. So if you put 10 to the power 11 solar mass, for example, here, you will find that the total average energy of the cluster will be positive. But positive energy means that the system is not bound. And this was the argument which was given by Fritz Zwicky in 1933 when he made a detailed study of the Coma cluster, that he found that for such high dispersion velocities and the baryonic mass n into baryonic mass of a typical galaxy cannot keep the Coma cluster bound. But the fact that you are seeing so many galaxies clustered together, unless they are physically bound, it will only a chance probability that you will see at random so many galaxies to be concentrated in a small region. And there is not and Coma cluster is not the only cluster. There are so many galaxy clusters that have been observed. That means that the galaxies in such concentrated form, making a overdense region of galaxies, they must be physically sort of in a bound state. And for bound state, you need the total energy to be negative. And Fritz Zwicky, therefore, correctly inferred that we are underestimating the mass of the cluster. If mass of the cluster is more than n times baryonic mass of the galaxy, then of course gravitational potential energy will be more negative and it'll compensate for the kinetic energy, because remember, kinetic energy goes linearly with mass of the cluster, n times m gal. But the potential energy goes as quadratic, is square of the mass of the cluster. So if the mass of the cluster increases slightly, this grows more than the kinetic energy, and therefore it can be bound as well as the virial theorem can be satisfied. All right, and so Zwicky, therefore, his analysis uh, implied that there is some dark matter which doesn't show up when you observe clusters by peering at them through telescopes. Then comes the other inference, namely, which follows from the flat rotation curve that I showed. Again, I'll go back to the slides again, but yesterday I talked about how Vera Rubin and her collaborators, they studied the neutral hydrogen clouds which are present far away from from a spiral galaxy, and by looking at the rotational velocity of the neutral hydrogen clouds, by studying the Doppler shift of the 21 centimeter lines coming from the neutral hydrogen cloud, she inferred uh, the presence of dark matter. How did she infer? After all, if a neutral hydrogen gas cloud is going around the center of a galaxy in a circular orbit, then the centripetal acceleration, which is square of the rotational speed divided by r, must be given by the gravitational field, which is gmr by r square, where mr is the mass enclosed within a radial distance r. Okay? Because we know from Newtonian gravity that gravitational field of a spherical body at a given point is due to uh, the total mass enclosed uh, within a distance of that point where we are measuring the gravitational field. And therefore, assuming, it's a good approximation, assuming that a galaxy can be treated in a spherical distribution manner, we can therefore write this equation that square of the rotational speed divided by r, which is the centripetal acceleration, is being provided by the gravitational field due to a mass, total mass present within a distance r from the center of the galaxy. And gmr by r square is nothing but the gravitational acceleration. So 1 over r, 1 over r square, so one of the r factor can be cancelled, so that v square rotation is simply gmr by r, and therefore v rotation is simply square root of gmr by r. What does this equation tell us? The equation number 8 tells us that when you start from the center of the galaxy, then the velocity, rotational velocity of a typical star around the center of the galaxy, when you are very close to the center, will be very tiny, because the total mass enclosed around the galactic center is very tiny. At the most, it has only a supermassive black hole, which is of the order of billion solar mass. But as you keep going outwards, as r increases, m of r also increases, because now as the spherical region size increases, you have to take into account the mass due to stars and the gas present. So MR also increases, and MR increases as density times R cube. So even if you take density to be constant, density times R cube by R, so R cube by R is R square, and square root of R square is R. So initially, the rotational velocity must increase as R. But when you leave the boundary of the galaxy, then M of R will not increase if the galaxy is only made out of baryonic matter. Outside the galaxy, you don't see any stars. So M of R will be constant, but then the rotational velocity must go down as 1 over square root of R. So if there is no dark matter, you would expect that the rotational velocity plot, that means if you plot rotational velocity as a function of the radial distance, then initially the rotational velocity will linearly increase with R. Then once you leave the galaxy, then the rotational velocity should fall off as R to the power minus half, or 1 over square root of R. But the actual observation that were made for the first time by Vera Rubin and her teammates found that instead of rotational velocity of these neutral hydrogen clouds falling as 1 over square root of R, for many spiral galaxies, the rotational velocity, they appeared to be constant. So at distances larger than 50 kiloparsec, the rotational velocity tend to be constant. What does it mean for the rotational velocity to be constant? If it has to be constant, then m of r divided by r for r larger than 50 kiloparsec must be constant. M of r by r can be constant only if m of r is also proportional to r, so that r gets cancelled. But what is m of r? M of r is the total mass enclosed within a radius r, and we are talking about now radial distances greater than 50 kiloparsec. If m of r by r has to be constant, it means m of r, which is roughly density times r cube, okay, density must go as 1 over r square, because density times r cube by r is density times r square, and density times r square is a constant, meaning at large distances the density must go as 1 over r square. But nevertheless, the fact that there are no stars, meaning that this matter for which density goes as 1 over r square at distances greater than 50 kiloparsec, this density must be coming from dark matter. So there is a dark matter halo around every galaxy, and the halo extends up to at least 100 kiloparsec, and from 50 kiloparsec to 100 kiloparsec, the density of the dark matter should fall as 1 over r square in order to explain the flat rotational velocity. All right. Now I will go back to the picture again. Right. So what we just now showed using very simple uh, physical consideration, using simple mathematics, is that the observed rotational velocities tend to be flat for distances greater than about 50 kiloparsec, while if the stars and the gaseous matter that we see using a telescope, they end here, then we would have expected that the rotational velocities of the neutral hydrogen clouds outside the galaxy should have should have followed 1 over square root of distance, but instead we are seeing that the rotational velocity is going flat, and hence we infer that there is matter even outside the baryonic matter of a galaxy, all right? Because the 21 centimeter line, note that our calculation, when r is very close, when r is small, that is, you are very close to the center of the galaxy, it indeed shows a linear rise, as I argued from our simple calculation. The problem happens when you go to larger and larger distances, then instead of 1 over square root of r fall of the rotational velocity, sometimes you actually see the rotational velocity to increase. But largely for most galaxies, the rotational velocity actually becomes flat after a certain particular point. So this is for the galaxy, elliptical galaxy M33. And that is the reason why we infer that there is dark matter around galaxies. And then we know that, as Zwicky had concluded, there is dark matter halo. Apart from dark matter halo around every galaxy in a cluster, there is a diffuse dark matter present throughout the cluster of galaxy. And this certainly is also inferred from the gravitational lensing that is seen, and in particular the bullet cluster, where we see that gravitational lensing requires that there be matter here and there be matter here. The matter here and matter here are not seen through telescope, but the matter here and matter here, which are shown in red, are seen through optical telescope. And that the fact that there should be matter here shown in blue, matter here shown in blue, they must be present in order to explain the gravitational lensing. And this shows that these are dark matter. They have overshot when the two clusters of galaxy collided. Because of the inertia of motion, the dark matter overshot. They went this way and the other went this way. While the baryonic matter, because of the viscosity, the velocities got damped out and they could not move further. And that certainly gives another corroboration to the idea that dark matter interact very weakly, and of course they interact via gravitation anyway. Right, so this is another gravitational lens system. If you take Abel cluster 2218, again you see that arches of light, which are due to, which is some kind of Einstein ring because of the bending of light of a source behind this cluster of galaxies. There are many further research work going in the field of dark matter. All I will tell you is that right now the evidence is that the baryonic matter, when you study the large scale distribution of matter in our cosmos, the baryonic matter seems to be about 4 to 5%. That means the standard matter that we are made of, the total budget of this standard matter, baryonic matter that we are made of is only 4 to 5% of the total matter in the universe. The dark matter, which is expected to be, the dark matter particles are supposed to be moving at non-relativistic velocity. That's why it's called cold dark matter, because from the structures that are formed, one would say that largely the structures arose only out of non-relativistically moving dark matter particles, and therefore we call it cold dark matter. And cold dark matter appears to be about 23% to 25%. And there is another mysterious source whose presence has been felt through the observed late time acceleration of the universe, meaning there is some source which causes anti-gravity, and this uh, the source is referred to as dark energy, and we still don't know what that dark energy is, which causes anti-gravity and thereby makes the galaxies, the distance between different galaxies increase at an accelerating pace. On the other hand, cold dark matter have attractive gravitation. So although both are called, both have been prefixed with the word dark, but dark energy and dark matter are distinct in the sense dark energy causes only repulsive gravity, while dark matter has attractive gravity. So, in other words, our universe is dominated by dark entities. So I'm sure many of you are fond of dark chocolates, but unfortunately, the dark entities I'm talking about, we don't know what the dark entities are, and these are active areas of research. And as I said, the evidence, observational evidence for late time acceleration of the universe, namely the fact that a typical scale describing the expanding universe, Hubble showed that universe anyway expands. The scale factor, a typical scale describe the universe, keeps increasing with time. That has been known since 1929, but it is the work of Perlmutter, Brian Schmidt, and Adam Rice. By studying the type 1a supernovae, they showed that this typical scale not only is increasing with time, but the rate at which it is increasing with time itself is increasing. And therefore, there must be some crazy matter which causes repulsive gravity, which has been christened as dark energy. And this dark energy is like a, you can think of a spring which is always trying to, it's like a compressed spring which wants to expand out, causing repulsion. But we still don't know what exactly this dark energy is made of. So dark energy causes gravitational repulsion, while dark matter causes gravitational attraction. And it would be very interesting in the coming 10 to 20 years when finally one would be able to find out what these dark matter particles are and what is the source of this gravitational repulsion. That is what the dark energy is actually. So here is again the budget. So roughly the stars have baryonic matter and they constitute 0.5% of the entire matter, while hydrogen and helium, they constitute about 4%. By the way, these 4%, 0.5% are by mass or by weight, not by number or by volume, but it is 0.5% by mass, 4% by mass, while the neutrinos, they constitute about 0.3% of the total mass. There are heavy elements. We know heavy elements are there on Earth. We know that iron is found, gold is found, uranium is found. The heavy elements, the percentage is very tiny. It's about 0.03%. Dark matter is 23 to 24%, and dark energy is 68 to about 70%. This is a pie chart of the fraction of mass which are associated with different categories. Dark energy, by the way, dark energy, how did one conclude about dark energy? It is by looking at the apparent magnitude of type 1a supernovae versus the redshift. I don't want to go into the detail, but whatever you have learned so far, the apparent magnitude, absolute magnitude, here what is being plotted is actually apparent magnitude minus the absolute magnitude of a type 1a supernovae uh, observed at different uh, distances. And we find that instead of falling in this line, it seems to be the apparent magnitude tends to be larger at large distances, indicating that the uh, the universe is actually accelerating. Anyway, I don't want to spend too much of time here, uh, except to point out that in order that you see accelerating universe, that means you have repulsive gravity. Repulsive gravity is allowed in general relativity, except that to generate repulsive gravity in the framework of general relativity of Einstein, the pressure must be negative. In fact, in order to generate repulsive gravity, energy density plus three times pressure must be negative. And there is something called a cosmological constant for which pressure is exactly equal to negative of energy density. Anyway, I'm just, for the sake of completeness, I'm talking about this. I don't expect that you will understand all these because these require studying full cosmology in the framework of general theory of relativity. Right. So, are there any questions so far? Because I covered stuff which might be somewhat unfamiliar, so it would be helpful if you have questions at this stage. Okay, so far there is no question regarding whatever I have taught, uh, but since today is the last lecture, on the coming Saturday, we will essentially discuss doubts so that um, before the exams, we have a good idea as to what are the possible sources of confusion, or if you have any doubt, etc. Um, remember, today is the last regular class. So if there is any question, please let me know now so that we can move forward. Yeah, Nancy Chanu is asking, uh, does repulsive gravity negate the notion that gravity is always attractive in nature? Very good question. Right. So, why do we say that gravity is attractive in nature? That is because of experiments. Experiments tell us that moon is falling towards earth. In fact, Newton discovered the inverse square law. Probably I had given asked you to calculate by looking at the acceleration that moon is undergoing and the acceleration of an object that is dropped near the surface of the earth. I had asked all of you to show that there is a inverse uh, dependence on the square of the distance. So the fact that gravity is seen to be attractive comes from experiments. And that is the whole idea of science. Science is not uh, imagining how nature should be. Science is about finding out what nature is actually like by doing experiments, by having observations done. So, as I tell my students, if I want to know about you, I have to ask questions. I can't simply look at you and start guessing everything, right? Your name, where you have studied, and so on. So on. In order to know about you, I have to ask you various questions so that I have some idea about you. Similarly, if I want to know what nature is, I have to do experiments. I have to do observations concerning natural phenomena. Doing experiments or doing observations are like asking questions to nature herself. So, when we do experiments, when we observe, we are actually asking questions. We are addressing these questions to Mother Nature. And from the results of our experiments and observation, we get an idea about the fundamental nature of our world, of our physical world. So, gravity being attractive was essentially inferred by looking at measurement. Whether it is object, when I drop, it is always falling towards the earth, the object doesn't go outwards, or similarly, moon going around the earth, therefore, the acceleration of the moon is always directed towards the center of the earth, tells that moon feels the attractive force of earth. Similarly, earth and other planets going around the sun tells me that earth, other planets, their acceleration, they are all directed towards the sun, or rather, to be correct, towards the center of gravity of the solar system. The center of gravity of the solar system is referred to as the barycenter. So, planets as well as Earth, they accelerate. The so-called centripetal acceleration is towards the barycenter, and therefore it shows that the planets and in particular Earth, they are falling towards the barycenter. And the fact that solar system and other stars are going around the center of the galaxy shows that gravity is attractive. Um, so all these observations and experiments told us about gravity being attractive. And we got used to the idea that gravity is always attractive. So if you have two positive masses, m1 and m2, the gravitational force is always minus gm1 m2 divided by r square, and the direction multiplied by the unit vector connecting the 2 point objects. The negative sign tells me that if M1 and M2 both are positive, that means the masses are positive, then gravitational force between them, as gleaned from several experiments and several observations, is attractive. Theoretical physicists, of course, they try to say, okay, what if I find tomorrow an object whose mass is negative? So minus gm1 m2 by r square multiplied by unit vector joining the two particles. If m1 is negative, then of course you get a positive gravitational force. So if you have a negative, if you have an object whose mass is negative, then it will repel positive mass objects. So from theoretical point of view, the Newtonian laws of gravitation, they also admit repulsive gravity, provided you get an object whose mass is negative. Theoretically, it is possible, except that so far, no one has found out any object whose mass is negative. If you find an object whose mass is negative, then you will become very famous. You actually will be awarded a Nobel Prize, because it will be so very different from whatever we have observed or understood so far. So, unfortunately, no one has discovered an object that has negative mass. But if you have an object whose mass is negative, then obviously, according to Newtonian laws, there'll be repulsion between a negative mass object and a positive mass object. Of course, there is um, uh, uh, another bizarre phenomena if you find a negative mass particle. What is that phenomena? Imagine that you have a negative mass particle, and if it has a velocity v, then its kinetic energy will be half mv square. But now m is negative. If m is negative, then kinetic energy itself is negative. And what is very strange is that more is the speed of a negative mass particle, more negative is the kinetic energy. Okay. So, in other words, if you have a negative mass particle moving with speed v, if you take away energy from it, meaning what? If you take away energy from it, its kinetic energy should become more negative. And how can the kinetic energy of a negative mass particle be more negative? It can happen only if its speed increases. So a negative mass particle will show a bizarre behavior that you take away energy from it and it will move faster and faster. So these are all strange phenomena associated with hypothetical negative mass particle, even in the framework of Newtonian laws. But when you learn general relativity, you will find that in general relativity, what causes gravity is not just mass or energy, even pressure causes gravity. And in particular, if energy density plus 3 times pressure of a substance is negative, then such a substance can cause repulsive gravity. It is another matter that we have not found a system for which energy density plus 3 times pressure is negative. And that is the reason why astronomers and cosmologists have postulated something called dark energy, for which energy density plus 3 times pressure is negative, so that it can explain the late time acceleration of the universe. Okay, there is one more question. There are more questions. Shubham asks, Yeah, so Shubham is saying that if dark matter and baryonic matter they cause attractive gravity, then why are the galaxies going away from each other? So as Hubble from his observations found that galaxies are indeed going away from each other, but galaxies going away from each other is same as when I throw a ball outwards. Although the Earth's gravity is attractive, if I throw a ball outwards with a large velocity, then the distance between the ball and Earth will keep on increasing. And in particular, if I throw the ball with a velocity either equal to the escape velocity or greater than the escape velocity, the ball will never return back to Earth. The ball will keep on going away from the Earth. So, before the dark energy business came about, people thought that, well, galaxies are moving away from each other because of the initial condition, because of the Big Bang. The Big Bang was so hot and dense that there was expansion. But the expansion would slow down because of attractive gravity. That was the idea before Rice, Schmidt, and Perlmutter discovered that, well, the expansion is actually not slowing down, it is actually getting accelerated. And that is the reason dark energy had to be postulated. So, just the fact that the galaxies are going apart from each other doesn't mean there is repulsion. What you have to ask is the rate at which galaxies are moving away from each other, is that rate slowing down or is it going up? Only that will tell us whether there is attractive gravity or repulsive gravity. Shivangi is asking, why does dark matter constitute large portion? No, I think there is some typographical error. Probably what she means is, why does dark energy constitutes large portion than the dark matter? Probably that's what she means. Yes, so that is an observed fact. These are based on observation. Why, for example, the baryonic matter is only 5%, while dark matter is 25%? No one knows really. It all depends upon what dark matter particles are. And only then, if we know what dark matter particles are, what constitutes dark energy, only then we'll be able to figure out why is the proportion of baryonic matter so minuscule in comparison with the amount of mass trapped in dark matter or amount of energy or mass equivalently trapped with dark energy. Because we still don't know what the nature of dark matter is, at the moment we can't answer as to why dark matter is so large in mass compared to the baryonic matter. Nancy Chanu is asking uh, whether dark energy necessarily have to be created from negative mass. As I mentioned, it is not required. As I told you, negative mass particles, uh, they have this bizarre phenomena that if you take away energy from it, they will move faster and faster. And such behavior leads to instability of matter, because matter will derive energy out of this negative mass particle, and the entire negative mass particle will decay to more and more negative energy, and the whole universe will explode because the rest of the matter will derive energy out of it and will explode. So, presence of negative matter particle, negative mass particles are actually not a good thing for physical theories, because it leads to an unstable universe. So there better not be any negative mass particle, because then the universe will simply explode. Particles will derive energy out of the negative mass particle, and the negative mass particle will go into infinite negative energy, while other particles will get infinite positive energy, and the whole universe is explode. So, for the safety or for the stability of the universe, there better not be any negative mass particles. Okay. But as I said, that in the framework of general relativity, after all, to study the evolution of the universe, one has to use general relativity, because general relativity, when the gravitational potential becomes larger than c square, you cannot use the approximate Newtonian gravity. You have to use the correct classical theory of gravity, which is general theory of relativity. And in the framework of general relativity, you can explain repulsive gravity by having a strange kind of substance for which energy density plus 3 times pressure is negative. Okay. All right. Shruti is asking that for a particle to exist, it must have positive mass. Otherwise, what can be the proof of its existence? A good question. Shruti, what is more important? How do we infer entities around us? So right now I am discussing with you the philosophy of acquiring knowledge, which is the area of philosophy which talks about how to acquire knowledge about nature is called epistemology. So in the framework of epistemology, we ask the question, how do we get to know about the world around us? So if I want to detect a particle, detect meaning see a particle or feel the existence of the particle, there must be some signal that is present. There is a transfer of a signal from what is being detected and the observer. That means a signal has to be transferred from an object that is present to the observer. And any signal that is transferred has to carry energy. That is what comes out from physics, that any signal which creates an effect in the observer must have energy. So, therefore, only those objects can be perceived which can transfer energy from itself to the probe. Otherwise, if the energy cannot be transferred from the object to a probe which is trying to detect the particle, we cannot know about the existence of particle. So positive mass is not required. What is required is that the particle must have energy. And you're right, energy at itself divided by c square is mass. So even if you have a negative mass particle, if it can send a positive energy signal, that means the signal will have positive mass, but the object itself can have negative mass, so that because it is sending a positive energy, therefore the negative mass particle's energy becomes more negative. But in principle, you still can have a particle with negative mass. All what is required is it should be able to transmit a positive energy to the probe that is trying to detect the negative mass particle. All right. Okay. So Ankit is asking why galaxies have random velocity in clusters. Very good question. Well, if the cluster was rotating, if there is a rotational motion like what we see in spiral galaxies, then of course the galaxies will be stabilized by their rotational motion. Or in other words, you can think of the centrifugal forces cancelling out the net gravitational attraction, and therefore galaxies which are rotating, they will not fall into the center of the cluster of the galaxy. But most clusters don't have much angular momentum, and therefore, in order the galaxies, they don't all fall into the center and become a huge black hole. The galaxies better be moving in highly eccentric orbits around the center of the cluster. And because a cluster, a galaxy cluster is spheroidal in shape, that means is not a flat disk like shape, it's spheroidal in shape. That means the eccentric orbits of different galaxies must be in different planes. And hence, all these eccentric orbit velocities are not correlated with the velocity of the eccentric orbits of other galaxies. And this is what we mean by saying that galaxies in a cluster, they have random motion. Each galaxy is moving in an roughly an eccentric orbit around the center. Remember, this is not a full elliptical orbit because they are also interacting with other galaxies, and also the gravitational potential is not 1 over r square. So therefore the orbit is not an elliptical orbit, but they are highly eccentric and highly random orbit because of the fact that each galaxy is interacting with each other gravitationally in a cluster. But no one has worked out the orbit of a galaxy in a cluster because it would uh, not be possible to do it analytically. It can be only done using computer simulation. Nancy Chanu is asking, what lies beyond the universe? Well, uh, universe, as we know, of course, this is all theory because uh, the observable part of the universe is only speed of light divided by the present Hubble parameter, c by h naught. Okay, and why is it so? Why should why is it true that we cannot observe at the moment a distance roughly beyond c by h naught? The reason is this. In yesterday's lecture, we saw that 1 over h naught, that is 1 divided by the Hubble parameter at the present epoch, is roughly the age of the universe. If 1 over h naught is roughly the age of the universe, then from the beginning of the universe, you ask yourself, from the beginning of the universe, what is the furthest distance any particle would have traveled? Now, we all know a particle can travel at the most with the speed 3 into 10 to the power 10 centimeters per second. This is something which special theory of relativity tells us. Special theory of relativity tells us the maximum speed any particle can have is 3 into 10 to the power 10 centimeters per second. And therefore, since the Big Bang, the maximum distance any particle could have traveled is 3 into 10 to the power 10 centimeters per second multiplied by the age of the universe. And the age of the universe is roughly 1 over h naught, where h naught is the Hubble parameter. And therefore, from this argument, it follows that maximum distance we can in principle see today is from those regions of the universe from which particles from the starting point of the Big Bang could have reached us. And since the starting point of Big Bang was about 13.8 billion years ago, The maximum distance from which these particles are coming to us currently is 3 into 10 to the power 10 second, 3 into 10 to the power 10 centimeters per second, multiplied by 13.8 into 10 to the power 9 times 3.16 into 10 to the power 7 seconds. Because 1 year is 3.16 into 10 to the power 7 seconds. So if you worked out the numbers, in fact, I'll give you a problem in the assignment based on it. If you work out the number, you will find that the maximum size today that we can observe is around 10 raised to power 28 centimeters. All right. So that is it's called the Hubble radius. The present Hubble radius. What is the physical meaning of this Hubble radius? This is the maximum distance up to which today, in principle, I can observe the universe, which is C into age of the universe. And please work it out. I will also ask you in the assignment sheet. Please work it out and you will find that the number is about 10 raised to the power 28 centimeter, which is same as 10 raised to the power 26 meters, or which is same as 10 raised to the power 23 kilometers. A very large distance. But so far, we find that there is no boundary of the universe. And therefore, the universe doesn't have an edge. Even if the volume of the universe is finite, but there is no edge. Imagine how can the volume be finite and yet there is no boundary. There is a two-dimensional analog. I mean, I can explain it using the analogy of a two-dimensional space. Imagine in two dimension a infinite sheet or infinite plane. The area of this plane will be of course infinite because it's extending everywhere. But you ask yourself a question: can I think of a two-dimensional surface whose area is finite but there is no boundary? If you tell me a circle, well, circle's area pi r square is finite, but circle itself is the boundary. But is there a two-dimensional surface for which the area is finite, but there is no boundary? The answer is yes, the surface of a sphere. As you know, the surface of the sphere of radius r, the surface area is 4 pi r square. It is finite. But the surface of the sphere has no boundary. Meaning what? If you start from one point on the sphere and trace out, if you take a pen on your globe or on your football and try to trace out, the tip of the pen will never go out of the surface. You will come back to where you started if you are following in a straight path. So our universe, similarly, if you take the three-dimensional analogy, the closed universe, for those models where the universe is closed, the total three-dimensional volume at any given point of time is always finite, but it doesn't have an edge. That means mathematically, if you keep moving straight ahead in a closed universe, a mathematical ray which is going straight will come back to itself in such a closed universe. But open universe, of course, open universe, they have at any given instant of time, three-dimensional volume is infinite for them. So they are anyway infinite system. And again, there is no, the question what is beyond the limit of the universe is also not of interest because anyway, there is no boundary of the universe. Regarding other universe that you are asking, well, in string theory and other theoretical models, people talk about multiverses. There are also other models of cosmology where there are uh, a universe can lead to another small baby universe and so on. But these are all theoretical ideas and they require higher dimension, higher spatial dimension to talk about multi-universe and the so-called uh, bulk of the brain world. The brain world is the three-dimensional brain, where brain meaning this brain is not BRAIN but BRANE, is a it's a part of the membrane, because in string theory there are multidimensional uh, ideas, and therefore people talk about our three-dimensional world residing on a three-dimensional brain, and there can be other uh, dimensions which would lead to different kind of universe. But remember, these are at the moment only mathematical models. There is no experimental confirmation whether there are multiverses or baby universes and so on. Shubham is asking, is there a star without having planets? Yes, why not? In fact, most of the stars around us, they don't have planets. And only those stars become very interesting which have exoplanets associated with them. As you know, that there is a telescope called Kepler telescope, and Kepler telescope has seen a large number of stars which have exoplanets going around it, and one or two of the stars, they exhibit exoplanet which are similar to earth, and astronomers are excited about them, because possibly those exoplanets which are similar to earth and which are in habitable zone, meaning the temperature of the planet is not so high that water will be in the steam form, or not so low that the water will be in frozen form. And liquid water is believed to be very important for genesis of life, and people are interested in such exoplanets. Shubham has asked, uh, how are we sure that there was only one bang at that time? Well, in Big Bang model, there is only one bang, but there are other models like the ones proposed by Jayant Narlikar, Burbidge, and I have also written a paper, a research paper way back in 1993 with Professor Jayant Vishnu Narlikar on mini banks. That is, the idea is that overall there is a steady state model, but there are locally small mini banks. And in our 1993 paper, Professor Narlikar and I, we talked about constraining such mini banks happening by looking at the gravitational waves produced from them. But these are not mainstream ideas, because so far observations, large number of observations are explained by single Big Bang phenomena. So work like gravitational waves from mini creation events, uh, the work that Professor Narlikar and I published, these are interesting ideas like string theory ideas. There is no experimental confirmation. Jay Singh is asking why planets don't collapse due to their own gravity. Very good question. When I talked about stars, I said the stars are in quasi hydrostatic equilibrium because of the pressure arising out of the gaseous substance. Because the stars are largely made out of uh, a fluid like plasma and gas, and they have the pressure, either kinetic pressure due to randomly moving ions, electrons, or atoms, or they can have pressure due to radiation themselves. For very massive stars where the radiation density is very high, the photons themselves contributes to the pressure that keeps a very hot star in quasi hydrostatic equilibrium. In the case of planets like Earth, Earth is a solid planet. Uh, the core, of course, is liquid. There, the pressure is due to uh, the solid pressure which arises typically due to Pauli exclusion principle. For example, the reason why you find it hard to compress a rock or a iron block is because of the Pauli exclusion principle. I don't want to go into details because that will take us to condensed matter physics. It is really the pressure arising due to Fermi energy level, where if you try to compress, the Fermi energy level increases and therefore you need more energy to compress. It is this pressure which keeps a solid planet like Moon is completely solid as far as we know, and Moon doesn't collapse under its own weight because of the pressure arising due to Fermi levels of the solid substance. Earth, the crust part of the Earth, the solid part of the Earth, of course, gets balanced by this kind of Fermi pressure. But remember, the temperature as you go deeper and deeper uh, into the earth, the temperature rises, and after a while, the temperature is so high that the matter in the core of our earth is a molten state. And largely, the molten liquid has lot of iron in it. And it is the liquid pressure, um, as you know, any liquid has a pressure, which of course arises again largely due to the kinetic theory. And it is this pressure which keeps a planet like Earth under equilibrium. Gaseous planets like Saturn, Jupiter, these are, of course, in quasi hydrostatic equilibrium because of the gaseous pressure. But solid planets like Earth, Mars, asteroids like objects, satellites, they are stable because of the pressure arising out of the Fermi surface, Fermi energy level. Shubham is asking why International Space Station gravity is zero, while at the orbiting radius of ISS, the Earth, gravity of the Earth still works. Well, it depends on who is measuring the gravity. For a freely falling object, so uh, if you go in a plane aircraft, as long as the aircraft is not freely falling, you feel your weight in the aircraft. So when you are flying, you walk about in your plane as though you're on the surface of the earth, feeling the gravity. But if your aircraft starts freely falling, then you will become weightless. You will not see the gravity at all. So if you measure the gravity when you are in an aircraft that is freely falling, then the measured gravity will be zero. On the other hand, I will see the freely falling aircraft to be accelerating towards the earth. And I will say, well, the aircraft is accelerating towards the earth because of earth's gravitational force on the aircraft, while you inside the freely falling aircraft will say gravity has been completely nullified. In fact, the first person who used this idea to create a fundamental theory was Einstein himself. Entire general theory of relativity is based on this idea that no matter how strong is gravity, you can always choose a frame of reference in which gravity in a small region in the frame for small duration can go to zero. Such frames are called locally inertial frames of reference. And this hypothesis that in a locally inertial frame of reference, gravity is completely zero is the basis of general theory of relativity. Entire general theory of relativity is based on the assumption that a freely falling local frame of reference, in such a frame, gravity becomes zero. If you want to learn very simply about these ideas, then just type in the Google search general relativity for pedestrians, first 6 lectures, and you will see my article. The first section I have described physically, uh, the whole thing that I described, that how it is the local inertial frame of reference in which gravity disappears, led to the full framework of general theory of relativity. All right. I think I will not introduce further topics because we are having only 25 minutes more. It will not. I'll not be able to complete any discussion on a new topic. But no harm. After all, I have completed 90% of the syllabus. So I am happy that even in the online mode of teaching, I have been able to cover 90% of the introductory astronomy course. So what I will do is I will send you the PDF of the notes that I flashed um, uh, in the lecture, namely about dark matter, cluster of galaxy, rotation, velocity, um, and then I will also send you the last um, assignment set in the evening. And on Saturday, we will meet either at 10:30 or at 11 o'clock, and we'll have a full Google Meet discussion on any doubt you have. Okay. So I think I will stop now. I will end the broadcast. I will send you the PDF of the file that I showed to you, and then I will also send you the last assignment set, and we will discuss on Saturday, coming Saturday, further. So all the best. Stay safe, and we will meet again on Saturday. So goodbye. I will now end the broadcast.